But the Doppler effect doesn't just affect light, it affects any waves. And a really good example of that is sound waves, okay? If something is coming at you, its sound gets affected by the Doppler effect. The wavelength of the sound wave gets shorter if the object's coming at you, and if the object's going away from you, the sound wave gets stretched out and it gets a longer wavelength. And you probably have experienced that one, because it turns out with sound waves, you don't have to go very fast to experience the effect. With light waves, you probably have never noticed something coming at you looking blue and something going away from you looking red. But that's because most human speeds are not fast enough to see that, right? But with the sound effect on Doppler effect, it does happen. Because, again, if the object's coming at you, its sound will be a shorter wavelength. And do any of you guys happen to know what we hear different wavelengths as? I'm going to kind of expect probably not. So I'll go ahead and tell you. If you're listening to a sound with a very short wavelength, it's a high pitch. It's up here. That's a high-pitched sound. That's a short wavelength sound. Okay? Sorry for the volume. Anybody want to take a guess what a long wavelength sound is going to be? Sorry, headphone users. Does anybody want to take a guess as what a long wavelength sound is going to be? Yeah, a long wavelength sound is a low note. So, high pitch is a short wavelength. Low pitch is a long wavelength. Okay? Now. Sorry. Now, have you ever heard like a siren coming at you? Like, let's say there was a cop car driving by, okay? Let's say a cop car was driving by. Hopefully not like to get you. Let's hope it's not like for you. But let's imagine like a cop car was coming by. You can tell when it passes, even if you can't see it, by listening to it, right? So imagine that cop car coming by. When it's coming at you, its light and sound get squished up. So that means it's going to go to a higher pitch. So when the cop car's coming at you, it's like, wee, 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 wee. And when it passes, it's wee, 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 wee. Same thing with a train, right? It's wee. On the way in, it's high pitched because the sound is squished up. And on the way out, it's low pitch because it's the sound is being stretched out. And they'll actually do that in like cartoons and movies to fake motion. They'll do that Doppler effect on the sound. And what I'm getting at here is that also happens with light, right? It also happens with light. So like, I wish they would make a really realistic Superman movie. Because like imagine you were in trouble. And you call out like, Superman, help me. And then like miles away, Superman's like, oh, someone needs help. I must go save this citizen. And so he comes in at you at like half light speed. Now, let's figure this out. If Superman were coming at you really, really, really fast, what should happen to his color? What should happen to the color of his face if he was coming at you at like close to light speed? What would happen to the color of Superman's face? According to this model here. Well, he would definitely look blurred. But the color of his face would change blue. Superman would be going fast enough that you'd actually be able to see his color change. His color would turn blue because he's coming at you really fast, And what would happen to his voice? His voice should go really high pitched. It's like if Superman was flying at you at almost light speed, as he's flying in, and if he said like, "Don't worry," it would come out as, "Don't worry! Watch out, I'm coming for you!" If we were making a realistic sci-fi movie of Superman, that would be what we would expect. He would turn blue, and his clothing would turn purple because his clothing's already blue, and so it would need an even shorter wavelength. His clothes would turn purple. Yeah, he'd come in and be like, "Hey, don't worry!" And then you'd be like, "Ha ha ha ha, Superman, you sound like Mickey Mouse, Superman." And he's like, "No, I'm not, ha ha." Maybe he'll get kind of his feelings hurt, and he'll leave. And as he leaves, he's like, "Fine." He turns around and flies away. He will turn all red, and as he flies away, he would be like, "Oh, yeah, never mind then. Aw, you're mean." So keep that in mind. There's a certain kind of person who goes and sees a sci-fi movie or a superhero movie and they complain all the time of like, "It's not realistic. Oh, I don't like it because it's not realistic." If we made a actually realistic sci-fi or superhero movie, it would just suck. It would just be a terrible movie. Why do you need that for your sci-fi movies? Just whatever. You just like learn to chill, man. Okay? Anyway, final thing I want to say about this. Final thing. I hate the word blue shift and red shift because they're misleading. And we kind of got into that a little bit when we were talking about Superman just now. If this was a blue light bulb, then a blue shift wouldn't turn it blue, right? If this was a blue light bulb, in order to be a shorter color, what color would you see in that case? If this was a blue light bulb and you needed a little bit shorter, what kind of colors would you see? What's even shorter than blue? Yeah, like your purple colors, your indigo and violet, right? Your purple colors. So if that was a blue light bulb and it got blue shifted, you would see purple, but we'd still call that a blue shift, okay? So blue shift doesn't necessarily mean you're actually going to see blue. It just means that the color you're seeing is shorter than the real color. And on the other hand, red shift doesn't always make you see red, right? If this green light bulb was moving away from you kind of slow, you might see yellow, but we would still call that a red shift because it's longer than what you actually see. So it's probably better to, if I were naming these, I would call this short shift and this long shift because that's what they really mean. Yeah, that's a good joke. Now, check this out. Let me give you one last example of that. What if this was an infrared light bulb? Remember, infrared is too long for us to see, right? If it's an infrared light bulb, you wouldn't be able to see the light coming from it because it's too long. But if you took that infrared light bulb and moved it at you really fast, then the infrared light could get shortened until it just becomes visible. But what color would it look? It would look red, because red is the first color we can see on the long side, right? It would turn red. What would we call that? Would we call that a blue shift or a red shift in that situation? If we took an infrared light bulb and made it come at us until it got shortened into red light, what would we call that? So right here, this is why I hate the terms. we would still call that a blue shift because the red color you see is shorter than the infrared it started at. That's why I said that blue shift probably should just be called short shift. If the color you see is shorter than the real color, that means it's coming towards you and it's a blue shift. And if it's longer than the real color, that means it's going away and it's a red shift. Okay, now, here we go. Putting it finally through to just hammer it home. What will all of this look like in the spectrum? Here's the final picture from the book. There we go. Okay. Now, what they've done here, someone's asking, why did they have to use a green light as the basis? I think you probably do everything based off of a green light, because if you look at all the visible colors, green is kind of the middle. So it's easier to tell going one way or the other off of a green light because you've got enough visible light on both sides. And so I think that's probably why it became the standard for that system. Okay, now, good question though. Now, check this out. This right here is the spectrum of an object that is sitting still. Just like they took some random object and they took its spectrum and it looked like this when it was sitting still. When they moved the object, it looked like this. So let's just look at this right here. Now check this out. Which direction did all of the lines go? They all went to the right, right? They all went towards red. So is this object moving away from us or towards us? All of the colors got shifted to longer colors. Longer is to the red side. So is this object right here moving away from us or moving towards us? Moving away. Okay? How about this object? This object, those lines are even more to the left. So what's this object doing? That one's also away. That one's also away, but what's the difference between this one and this one? Can you tell which one of these is going faster? If this is what it looks like when it's not moving, and both of these are moving away, which one is moving away faster? 2, because it's shifted more, right? Okay, and now remember, this is the original not moving spectrum. These two are both shifted to the left. See how the whole pattern is moved towards this end? What are both of these objects doing? Yeah, this is what we see when the object moves towards us. The whole spectrum moves to the left. And which one of these two is moving away from us? Towards us. So which one of these is moving towards us the fastest? Yes, that is correct. That is correct. This one, because it is shifted more to the left,